So today, actually all this week, we're really talking about covalent bonds. And this week, basically what's happening is each day, we are dealing with a different way of modeling molecules. So different ways of representing a molecule. Yesterday, or Monday, we had planetary models. And so you built these planetary models, and you did things like say, oh, like here I have an oxygen, and I can see, I can see my planetary model. I've got the electrons in the inner shell, I've got the electrons in the outer shell, and then you use those to assemble things to make molecules like so. So yesterday, we did planetary models. Today, we're going to use Lewis structures. Lewis structures have a huge advantage over planetary models for molecules specifically, because molecules, especially molecules that use covalent bonds, can be huge. And very quickly, if you're trying to draw planetary models of molecules, it can just get overwhelming and it's really hard to make the pieces fit together neatly. Whereas with Lewis structures, because everything is so much more stripped down, all you have to deal with is the element symbol in the center and the valence electrons in your 4 quadrants around it. It's way easier to draw really big molecules. So today we're going to be focusing in on Lewis structures, and then tomorrow we're going to be working with mods, right? Things like this. So let's start with just a quick review of what we know about how we build molecules and why things build molecules. So we're going to talk about what it takes for atoms to come together to build a stable compound, to build a molecule that can actually exist in nature. We are going to talk about how covalent bonds specifically let us reach stability. And we're going to talk about how to use Lewis structures to draw out these molecules. So first off, what does an atom need to be stable? There's 2 things that need to be true in order to create a stable molecule. The first is that each atom in that molecule needs to end up with a full outermost electron shell. Or empty, right? Things like hydrogen tend to empty out. So for ionic compounds, that happened with things either stealing electrons or giving away electrons to fill in or empty out their outermost electron shell and follow that octet rule. For covalent compounds, this happens by sharing, right? Atoms will share electrons so that everyone ends up with a full outermost electron shell. So covalent bonds do this with sharing. Ionic bonds do this by stealing or giving away. The second thing that has to be true to create a stable molecule or chemical compound that can actually exist in nature is that we have to have something that ends up being neutral as a whole. So for ionic compounds, that might mean, like, let's say you've got lithium fluoride, where your lithium cation has a charge of +1, and your fluoride anion has a charge of -1. That would be 1 lithium and 1 fluoride. But if you have lithium oxide, where your lithium ion is +1 and your oxide anion is -2, then you would need 2 lithiums to balance out that 1 oxide. So with ionic compounds, we have to really make sure that what we ended up with is neutral, it's the same number of positives and negatives. For covalent compounds, every atom has the same number of protons and electrons all the way through. So no matter how complicated the thing you build, if all you're using is covalent bonds, it's going to be neutral. So you don't really have to worry about this second aspect as much for covalent compounds as you do with ionic ones. So just a reminder from yesterday, a covalent bond is a pair of shared electrons. 1 unpaired electron from one atom, 1 unpaired electron from a different atom that come together, partner up, are paired with each other, and are shared between these 2 atoms. Those electrons are the covalent bond. The electrons are the covalent bond. So if I were to take planetary models, here's 2 hydrogens as planetary models, you can see each of them has an electron, and if these come together, like so, now it's like each of these hydrogens has 2 valence electrons. They become happy. You can see that up here. Hydrogen with a valence electron, hydrogen with a valence electron. They come together, they share. The thing that's important to understand about this is that both electrons belong to both atoms. Those electrons are actually going to be orbiting both nucleuses. And it's that attraction between the electrons and the nucleuses that holds these atoms together and keeps this together as a molecule. So here you can see there's those 2 valence electrons that are shared, and they're actually moving back and forth between the 2 atoms. So these 2 atoms are bonded to each other to create a molecule. And they count as belonging to both atoms. Questions so far? That's a covalent bond. So here's a slightly more complicated example. Here we have water. If I were drawing a planetary model of oxygen, it would look like this, right? We've got 2 electrons in that innermost shell and 6 electrons in that outermost shell. So 1, 2, 3, 4, and then I can make pairs, 5, 6. So we have 2 unpaired valence electrons. Each of these unpaired valence electrons can make a bond. So oxygen, whenever we see a model of oxygen in a molecule, it's always going to end up with 2 pairs of electrons and 2 bonds if it's part of a molecule. Because each of these unpaired electrons is going to partner up with an electron, an unpaired electron from a different atom, and form a bond. So here we have those hydrogens. Each hydrogen has 1 unpaired electron. So each hydrogen can make a single bond. And so it's going to come together, right? Snap on, and we can create a molecule out of this. So here we have a completed water molecule. 2 hydrogens, 1 oxygen. Something I want to point out, how many bonds can a single hydrogen atom make if it has 1 unpaired electron?
2.
It's got 1 unpaired electron, which can partner up. So it can only ever make 1 bond. Can hydrogen ever be in the middle of a molecule?
No.
It can never be in the middle of a molecule because it can only form 1 bond. So wherever it goes, it has to be on the outside. The more bonds an atom can make, the more central it's going to be. As a general rule, whenever we're trying to figure out how do we build this molecule, take whatever can form the most bonds, put that in the very center. The things that can form the fewest bonds, like your hydrogens, those are always going to go on the outermost edge. So you start from the center with the things that can form the most bonds, and you work out from there. Yes, Naya?
So atoms with 4 valence electrons will go in the middle no matter what.
Yes. So carbon is a great example of something like this. Carbon, which has 6 protons and 6 electrons. 2 of those electrons go in the innermost electron shell. 4 go in the outermost electron shell. Carbon tends to make 4 bonds. So it always goes in the middle of a molecule. To draw this as a Lewis structure, because that's where we're heading with this, I'll draw carbon just real quick for you. C for carbon, because we always start with the element symbol. Then we say, hey, how many valence electrons? We know that carbon is in column 4A on our periodic table. Being in column 4A means it has 4 valence electrons, and we always put 1 in each quadrant before we make any pairs. So looking at this, I can clearly see, oh, carbon has 1, 2, 3, 4 unpaired electrons. So how many bonds can a carbon make? Yeah, 4 bonds. In a molecule, carbon, you're always going to see 4 bonds coming off of it. Let's do water now. So let's think about oxygen and hydrogen as examples to begin with. Oxygen, what column of the periodic table is oxygen in? Lisa?
The 6th one.
Yeah, it's in column 6A, which means it has 6 valence electrons. So when we place those valence electrons, 1, 2, 3, 4, 5, 6. So we've got 2 pairs of electrons but also 2 unpaired electrons. These unpaired electrons are available to make bonds. So how many bonds will oxygen end up with, Gabby? It's going to end up with 2 bonds. And now let's look at hydrogen. Element symbol H. Raise your hand if you can tell me what column is hydrogen in. Let's go to Danny.
1A.
Column 1A, so it has 1 valence electron. So it's got this 1 unpaired electron. Raise your hand if you can tell me how many bonds can hydrogen make. Talia.
1.
1 bond. So if we think about a water molecule, let's draw what a water molecule would look like with Lewis structure. All right, so let's draw a water molecule. We've got 2 hydrogens and an oxygen. Of those, oxygen can make the most bonds, so let's stick that oxygen in the center. I'm going to do an O for oxygen, and it's got 1, 2, 3, 4, 5, 6 valence electrons. 2 places where bonds can happen. I want to be really clear. When you are drawing your Lewis structures, I want to see your bonds. They're going to come off of these quadrants, north, east, south, or west. I don't ever want to see a bond coming off at a weird angle, right? We're always going to keep things really neat and tight. So we've got our oxygen. We also have 2 hydrogens. So let me draw some hydrogens for you. I'll use a different color just to make it obvious. Here's my first hydrogen. It's got 1 unpaired valence electron. Here's my second hydrogen. It also has 1 unpaired valence electron. So when we draw a Lewis structure, if I want to represent a bond, if I want to say, oh, this electron and this electron, they are coming together to be shared and form a bond, what we do is we first fully erase, completely and totally, the electrons that are going to go into the bond. So that electron, they go away. They are completely erased. And then I draw a little dash between them like this. It's not a long line, it's a pretty short line. Just like that. Again, you'll notice it's coming off straight from the quadrant that I'm dealing with. It's between the 2 atoms. Same deal over here. I fully erase an unpaired electron from each atom, and then I draw a line. That line is the bond. This line represents 2 electrons. The electron from the oxygen and the electron from the hydrogen. So if I look over this, I can see, oh, how many valence electrons does this oxygen have now? 2, 4, 5, 6 from this bond, 7, 8 from that bond. So this oxygen has 8 valence electrons, which means it's happy. Oxygen needs 8 valence electrons to be happy. How many electrons does this hydrogen have? 2, because this bond represents 2 electrons. And the hydrogen has 2 valence electrons, which fills its outermost electron shell and makes this hydrogen happy. So every single atom in a Lewis structure needs to be happy. And again, happy, atoms don't have emotions, they have stability. It means that we've followed those rules for what an atom needs in order to be stable. It's got a full outermost electron shell. We're going to be talking this week about a lot of different models, and I just want to take a moment and show you how similar these models are to one another. So, let me grab some of these planetary models. Here I have an oxygen planetary model. You can see it's got those 2 unpaired electrons. With the planetary model, we can also see the innermost shells. Here I have a hydrogen, right? It's just got that 1 outermost valence electron. Those hydrogens can click on with the oxygen, like so. So that hydrogen is going to be happy, but the oxygen still needs 1 more bond, so we can bring another bond like so. This is now a stable molecule. Right? So this is how I would do the same thing as a planetary model. And I want you to notice, hey, this is actually really similar to what I've got here. Right? We've got the oxygen in the center and the hydrogens coming off of it. You see how that's really similar to the Lewis structure? There is one more model we're going to about, and that model is the mods. We're not going to really get to these in detail till tomorrow. But this mod is for water, and you can see it follows the same pattern. We've got the oxygen in the center and the hydrogen sticking off. So all three of these are ways of representing the same molecule, and we should be able to see the similarities between them. All right, so just to reiterate, when these atoms come together, they share valence electrons, and everyone ends up with a full outermost electron shell. So for example, chlorines have 7 valence electrons. There's one unpaired electron which can bond up with something else. We can have molecules made out of 2 atoms. We can have molecules made out of lots of atoms. But they come together, they share those electrons to make bonds.
Is that the methane gas that people mistake? So it's not more.
There is a methane. So carbon here, 4 hydrogens coming in. So CH4 is methane gas. Methane gas is the major constituent in like natural gas. If you have a gas burning stove at your house, then methane is most of what's being burned. It's not everything in there. There's like the gas coming through your gas line is a mixture of lots of different things, but this is the major one. Is methane.
That's not the one that's mistaken for alcohol?
No, that would be methanol. I could draw you, in fact, we'll just as a little challenge for ourselves, remind me at the end of this lesson to draw you a Lewis structure for methanol, and I will do that. So, I'll do methanol at the end of this class just as a challenge. All right. So, the important thing here with covalent bonds is it's all about the valence electrons. Every unpaired valence electron can form a single bond. That means that Lewis structures are perfect for showing molecules using covalent bonds, because Lewis structures are all about those valence electrons. We typically use these for covalent bonds. It's a lot rarer to see Lewis structures for ionic compound. Isn't really the best way of representing an ionic compound, but a Lewis structure is perfect for showing a covalent compound. So let's do another example. I want to show you, let's do oxygen gas. So oxygen gas has the chemical formula O2, which means there are 2 atoms of oxygen in this molecule. Now, I already showed you a Lewis structure for just a single oxygen. We said, oh, oxygen is in column 6A, so it's going to have 6 valence electrons. 1, 2, 3, 4, 5, 6. 2 unpaired electrons, which means each oxygen can make 2 bonds. Let's do a second oxygen. 1, 2, 3, 4, 5, 6. 6 valence electrons, 2 of which are unpaired, and so we can make 2 bonds. So let's make some bonds. The first bond here should be pretty obvious, right? I can take this electron and this electron, fully erase them. We are not playing connect the dots. If I see those electrons still on your page, I will mark it wrong and put a bond in their place. Are these oxygens happy?
Yes.
No.
No.
No. How many valence electrons do these oxygens currently have? Danny?
7.
They've only got 7 valence electrons. Each oxygen needs another electron. And they can form another bond. So let's form another bond. We're going to form something called a double bond. Now, sometimes when people are doing double bonds, they have this impulse to play connect the dots and just be like, oh, I'll draw a line down here. We don't want to do that. Lewis structures should always be really neat and tidy. Make them as symmetrical as you can. Remove any stray marks. Make sure that it's very tidy. I will remove an unpaired electron from each oxygen, and then I put the bond directly in between the 2. So this is how I represent a double bond, right? I don't do this or connect the dots, right? That's not how we do it. It goes right here in between the two.
So the one with one line is a single bond?
One with one line is a single bond. With two lines, it's a double bond. You can also have triple bonds, but there is no such thing as a quadruple bond. So quadruple bonds do not exist. It puts too many electrons too close to each other, and they just pop apart. But a single, double, or triple bond is fine. Some additional things to bear in mind with your Lewis structures. Always put the things that can form the most bonds in the middle. Always make them really neat and tidy. You want to be working in those 4 quadrants. The bonds should always be coming off their own side. So like sometimes folks will try to draw something like this. Don't do that, that's messy, right? Instead, the bonds are coming off their own side. Sometimes folks will try to be like, come off at a weird angle. No, we don't want to do that. We want to come off north, east, south, or west. Make it really pretty and nice. And always check to say, hey, does everything have the correct number of valence electrons afterwards? Yes, check.
Are triple bonds common?
It depends on the element. Nitrogen oftentimes makes triple bonds in order to form nitrogen gas, which is a huge portion of our atmosphere. Triple bonds are really hard to break down. So the tighter things are bonded, the more bonds between 2 atoms, the harder it is to break down. All right, we are going to have some practice now in the class kit. So you have a class kit called Building Molecules with Lewis Structures. In this class kit, you are going to need to raise your hand to be checked. I have a particular note on the first slide. Just like pause, take your hands off your iPads for a moment. Hey y'all. On the first slide, draw the Lewis structure first, and then fill in the answer box for how many bonds. Don't try to come up with the answer before you've seen the Lewis structure. Draw the Lewis structure first, then tell me how many bonds it can make, based on how many unpaired electrons there are. You are going to need to raise your hand to be checked on all of these slides because they're all drawings. If you don't like to draw in class kit, you are always welcome to draw your answers on a piece of paper or on your whiteboard tables, and then take a photo of that if that is easier for you. I know that drawing on the iPad is not everyone's favorite thing. All right, y'all can get to work.